In this video, we are going to learn about survival analysis. In the first several slides, I will talk about difference between survival analysis with other techniques analyzing events versus non-event data. And I will show you how to draw Kaplan-Meier curves. And we will talk about elements in Kaplan-Meier curves such as median or mean survival time. And finally, we will use SPSS to draw Kaplan-Meier curves comparing survival between 2 groups, 3 groups or more. And lastly, I will show you how to edit your Kaplan-Meier graph by truncating time. Survival analysis is also called as time-to-event analysis. Survival analysis is a method often used in a cohort study where you observe not only whether a patient died or not, and also when they die. Therefore, the outcome variables involved in survival analysis is binary events or no events, and then time from the study enrollment to the point when event occur, which is a continuous variable. So you need to have these 2 variables. And survival analysis is not just limited to analyzing risk for death. You can use survival analysis to analyze any binary event. And for example, in the field of economics, typical applications of survival analysis is time from unemployment to re-employment. So we could use survival analysis to analyze time to onset of disease, or time to remission to disease or recurrence of disease. So there are many binary events and you can apply. This table is showing what happened over time in 10 patients from ID 1 to ID 10. Person with ID number 1 was followed for 8 days and died during 8th day. Okay. And the patient number 2 was followed for 4 days and died on the 4th day. Person with ID number 9 was followed until the study end, which is 12th day. Okay? And as you see, 9 patients experienced outcome events, which is death, and 1 patient was observed without event. And special technical terminology we use for this person observed without events is called censored. So we can say ID number 9 person was censored at the study end. And this is the ideal situation where patients were observed until event occur. And a patient without events, they were followed until the study end. So you have a complete follow-up. And when we describe risk over time, what you can do is compute total number of patients with events up to each day. So in this case, and you can see the proportion of deaths up to day 2 is 10% and day 3 is 20% because you have 2 people out of 10 die at 3rd day. And by day 5, and you have 1, 2, 3, 4, 5 patients, so 50% experienced death. Okay, and then at the end of the study, you have 90%, 9 out of 10 experienced the study. So if you want to describe change of risk over time, what you can do is you can simply apply binary analysis, proportions, compute proportion at every single day, and then you can plot that on the graph. So this is one way to describe what happened over time, how risk change over time. Although the challenge we have is in the clinical study, you could have a situation, a subject moved to another place, and therefore we do not know what happened to this patient after day 5. And or the ID number 3, this person, we collected so many phone numbers, but we couldn't reach this person with any number, so we lost the contact. So we don't know what happened to this patient after day 3. Person number 6, person came to the study toward the end of the study, so we couldn't follow longer than 4 days. And person number 7 refused to participate in the study in the middle of the study, so withdraw from the study. And person number 9, this person was in fact followed until the end of the study, but we lost the medical record after day 6. So we couldn't identify what happened to this person after day 6. So these types of censoring occur very oftenly in our clinical research. In such a case, what happens if we simply count number of patients who have events up to each day, okay, and we have this blue line. And since we don't really know what happened to the patient who were censored in the middle of the study, and we do miscount events among censored patients, and resulting in underestimation of risk. So in this data, so this is similar to a data you'd collect unless you have study with perfect follow-up, and you count 5 patients died out of 10. Therefore, cumulative event rate would be 50% instead of 90%. So this is a challenge we face. Therefore, we needed to develop the method which could account for this underestimation of events. So how we could count those events we could capture if we follow everybody until the end of the study. So in survival analysis, and I said we require 2 variables, and one is time and one is event. So event is simple. For the person who without event you code as 0, and person with event you code as 1. And person who has event, time variable would be time when event was observed. So in this person number 2, and time to death is 4. Okay? And the person who did not have event, and time would be the time at the last scene. So this person was last seen at day 5 and then lost and then moved to another place. So we don't know what happened after day 5. So you put the 5 here. Okay? So using these 2 variables, we are going to conduct survival analysis. In survival analysis, and similarly to rate analysis, are suitable in studies with which follow-up time vary among patients without events. And these methods were developed to prevent from underestimation of event rate due to censoring. So let's talk about how we can apply rate computations to estimate what happened to patients who are censored. Before we talk about how to compute Kaplan-Meier estimate, and let's review a rate calculation and see if we can use a rate to account for underestimation of risk due to censoring. And rate is computed by dividing number of subjects developing outcome by total follow-up time for the subject in the cohort. We count 1, 2, 3, 4, 5 events, which we put in the numerator. And let's count total number of follow-up days. So first person has 5 days of follow-up, and second person have 4 days of follow-up, including a day with event, and the third person have 3 days. So we add these follow-up for 10 patients, and we have 49 days. And rate is obtained by 5 divided by 49, and which is 0.102 per person day. So this is interpreted as if you follow 1 person a day, you'd expect 0.1 person have an event. That means daily risk of dying is 10.2%. Okay, for each day, 1 person have a risk of dying by 10.2%. So using this 10.2%, which we called as a hazard, which is instantaneous risk of event, and every day this patient has 10.2% risk of dying. Okay, so using a hazard, let's compute the probability of this person being dead after 3 days. In comparison to hazard, we call this the probability of being dead after 3 days as cumulative percent of events. Okay? And cumulative percent of events can be computed by 1 minus probability of this person not being dead after 3 days. So for each each day this person has 10.2% of risk of dying, which means each day this person has 89.8% probability of surviving. So this is 1 minus 0.102, which is 89.8%. And so in order for this person being survive at the end of day 3, this person have to survive each day. So you multiply 0.898 3 times. Okay? So this part, which is 73%, this is the probability this person survive after the end of day 3. Okay? And 1 minus that provide probability of this person being dead after 3 days. Okay, which is 27%. And we call this probability as a cumulative event rate. Okay, whereas probability of this person dying every day at each day is hazard. We call it hazard, which is 10.2%. Okay. So these two are very important terminology we use in survival analysis. So please make sure you understand the difference between the two. So let's review what is a hazard. Hazard is instantaneous risk of event. In this case, risk of this person dying at each day, which is 10.2%. And what is the probability of this person being dead after 3 days, which we call cumulative probability of dying, and that is 27%. So for day 1, and you do 1 minus 0.102, and you plot the probability here. And then day 2, you do 1 minus 0.898 to the power of 2, and you plot and then that value here. And for day 3, cumulative probability of death is 1 minus 0.898 to the power of 3, and day 4 to the power of 4, and day 5 and power of 5. So if you plot this cumulative probability of death, then you have a green curve. So green curve is actually higher than the cumulative probability. You simply count number of deaths divided by 10, which is a blue line. Okay, so using a rate, and we somehow estimated and what happened and among people who aren't followed long enough, and then cumulative probability of death is estimated higher than the blue line. Okay, let's compute Kaplan-Meier estimate. So we are going to use the same data set. We have 10 patients. Let's compute Kaplan-Meier estimates. And Kaplan-Meier estimate cumulative probability of survival. So you start with 100% patient being survived toward the end of the study, and it will decrease to a lower level. So we compute the cumulative probability of surviving. Or if you flip Kaplan-Meier curve, you can compute cumulative probability of dying up to the time to each day. And this plot indicates cumulative probability of survival, which is 90% at day 2. And this point presents cumulative probability of survival, which is 55% at day 5. Okay? So first thing you do in computing Kaplan-Meier estimate for cumulative probability of survival is you put the days and where either events or censoring events occur. So here what I put is day 2. And we have total of 10 patients at the beginning of day 2. And at day 2, we have 1 person died, okay? And no one was censored. At the beginning of day 3, we have total of 1, 2, 3, 4, 5, 6, 7, 8, 9. So we don't count person who experienced event here. So we have total of 9 patients at the beginning of day 3. And then at day 3, and 1 person experienced events. And then also there's another person, and this person was lost by the end of day 3. So you put 1 here. There is event of censoring occur at day 3. Okay? And at the beginning of day 4, and you exclude people who already have event. So we have 2 people with event and 1 patient censored out. So you have 7 patients at the beginning of day 4. So let's count. 1, 2, 3, 4, 5, 6, 7. And of those, there was 1 event observed on day 4, and then also 1 person was lost during day 4. Okay, so it's censored out after day 4. So you have 1 event and 1 censoring here. And at day 5, at the beginning of day 5, we have 1, 2, 3, 4, 5 patients at the risk. And of those, we have 1 event and then also 1 person are lost after day 5. So censoring occurred during day 5. So you have 1 event and 1 censoring here. And that leaves next time point, which is day 6. And we have 1, 2, 3 people at risk at the beginning of day 6. And there was no death. And 1 person was censored at day 6. And at day 8, of 2 people left in the risk and 1 person experienced event. And then finally at day 9, and then last person was censored. And last person was censored, and then therefore there was no one left after day 9. Okay, so after you create this part of table, okay, and then we start computation. And computation involves estimating hazard, which is instantaneous risk of dying. What is the probability of each person die at each time points? Okay, we need 1 minus hazard, which is probability of a person survive at each time point. And then last 2 columns are for cumulative probability. So we compute cumulative probability of survival, which is probability of a person being survived at the end of each day, and 1 minus that provide cumulative probability of dying, which is the probability of a person being dead by the end of each time points. So let's start with hazard. So hazard is computed as number of events divided by number of people at risk. So you do 1 over 10. Okay, and then at day 3 you do 1 over 9. And day 4 you do 1 over 7. And day 5 you do 1 over 5. So this is the probability of person die at each time point. And then you do minus 1 minus of that give probability of a person survive at each time points. Okay, so you have for day 2 you have hazard of dying, which is 1 over 10 and 10%. So you have probability of survival at day 2 is 90%. And cumulative probability of survival would be same for the first row. So this is 90%. Okay, and second time point, which is day 3, and cumulative probability of survival. Okay, in order to survive by the end of day 3, and then person have to survive at the end of day 2. So what you do is probability of surviving at the end of day 3 is product of probability of a person survive by the end of previous time point times probability of this person survive on day 3. So you take a product of these two, and that become cumulative probability of survival by the end of 3 days. And similarly, in order for a person to survive at end of day 4, this person have to be survive at the end of day 3 and also survive on day 4. So you take product of these two numbers, and that become probability of surviving at end of day 4. And the same thing, in order for a person to survive at until end of day 5 is product of a person being survived by the previous day times this person being survived on day 5. So okay, you multiply this number and this number, and that provide this number. And then you repeat this process to all the time points where events occur. For the time point and where the only censoring occur, as you see, it does not change probability of surviving. So, right, because probability of death at that day would be 0, and 1 minus of that would be 1. So you simply multiply cumulative probability of survival at the previous day and times 1. So at the time point, only censoring occur, and you just carry over cumulative probability of survival from previous time points. So therefore, Kaplan-Meier estimate change its value when the events occur. Okay? So here is events, here is another event, and here is another event occur. And then cumulative probability of dying, and you simply reverse this survival plot. So 1 minus this will provide the cumulative probability of dying. Okay, so this column is 1 minus this column. On this table, each time point we have only up to 1 event occur. There is no time point you have 2 or more deaths occur. And when you look at this Kaplan-Meier plots, and you see there is a bigger drop here than drop here. So why degree of drop is different? And because at this point, and you have only 2 people left. So 1 death actually contribute to 50% of change. So we have to be careful. Magnitude of drop is not just a function of number of events. It's also a function of number of patients and left at each time point. Okay, so let's review. We had 1 event occur among 10 patients in the risk set, and therefore cumulative probability of survival be 90%. And at day 3, and cumulative probability of survival, the probability of this person being survived end of 3rd day is a product of this person being survived. Product of this person being survived at the previous day, which is 0.9, times this person being survived on 3rd day, and which is given by 1 minus 1 over 9. So product of that gives cumulative probability of survival at the end of day 3. You keep taking a product and cumulatively taking product, and therefore we call this as a cumulative survival. So when I plot Kaplan-Meier based cumulative probability of death and compare with other method, and purple line is Kaplan-Meier based estimate. So as you see, this gives estimation larger than the number. You simply take proportion of deaths over 10 people, total number of patients being followed. So therefore Kaplan-Meier, similar to rate calculation, and Kaplan-Meier estimate does give a number which consider and what happened among people who lost to follow without observing event. So the final percent of death based on Kaplan-Meier curve is 73%. But you know only 5 people died in 10 patients, so that's 50%. So you know why 23% increase happened with the Kaplan-Meier estimate. So this Kaplan-Meier, so the method estimate inflate risk, assuming what would happen among the people who are censored, and if they stayed in the cohort longer. So that's why cumulative probability of death is larger than taking proportion. And censored observations are counted. Let's think why this inflation of risk happened and how the method dealt with censoring observation. So when each time and the patients are censored, they are left in computing number of people at risk. Although at the next time point they are taken out. And you start with 10 patients and then 1 person died. And then next time points in day 3, and you have 9 people. And then 1 person's censored out during day 3. So day 3, this person stayed in the risk set, although the next time point and number at risk becomes 7, so this person was taken out. So censoring observation does not really change directly change cumulative probability of survival, although So in the Kaplan-Meier plots, and this tick mark indicate when the patient is censored. So when censoring occurs, Kaplan-Meier curve does not drop because it does not really change risk of death, right? Although when at the next time point where the events occur, and these censored patients are taken up from denominator. So for example, if you start with 10 people and then you keep losing one patient at a time, and it does not change Kaplan-Meier estimate, although at the last point and you have only 2 people left, and then you have one event occur, then Kaplan-Meier curve drop by 50%. What the censoring influence on the Kaplan-Meier estimate is by taking up from denominator. So let's think what excluding censoring patients from the denominator means. And for example, among 10 patients and we lost 3 patients at the subsequent time point and one event occur. So when we compute the hazard at the subsequent time point, and we compute as 1/7, and we don't compute as 1/10. So if we compute the risk is 1/10, we are assuming these 3 people who are censored out from cohort did not experience events. And although we don't include them in the denominator, so we estimate hazards as 1/7. What does this mean? This means we are assuming and the risk for these 3 persons being dead at subsequent time point is 1/7. Therefore, Kaplan-Meier method does deal with censoring by imputing events among censored patient, assuming censored patient was at the same risk of a patient who stayed in the cohort. Kaplan-Meier curve provides several estimates. One is time to events, median time to event. A median time to event is obtained. The median survival time is computed as time, which corresponds to 50% cumulative survival probability. So if you draw a line, vertical line from 50% on y-axis to Kaplan-Meier curve, and where it crosses, and then you go down vertically, and then you can find a median time of survival. And similarly, you can find 25th percentile and 75th percentile. And in this case, 25th percentile value does not exist because the curve does not cross 25% line. And you can also obtain mean survival time. And mean survival time is the area under the Kaplan-Meier graph. So if there is no one had an event, and mean survival time would be simply total number of follow-up time, okay, which is a rectangle area, 1 times 12. And since so the more events occur early on, and you have less area under the Kaplan-Meier graph. So in this case, mean survival time is calculated at 6.3 days. And why we use Kaplan-Meier graph this way to compute mean and median survival time. And if you simply take mean and median of the follow-up time variable, 4.9 days for mean and 4.5 days for median, right? And which both are clearly shorter than 6.3 days or 8 days obtained from Kaplan-Meier curve. And why is that? The Kaplan-Meier curve is a method to estimate what happened among patients who are censored, and if the event occur, if their follow-up would be longer. So the model actually inflates median and mean survival time by assuming people who are lost to follow or censored had similar probability of events. So if they stay in a cohort longer, how much events occur. And therefore, a median time to events are prolonged. And this is an example from one of my collaborative study. And we collect delirium happen in ICU among mechanically ventilated patients. So we presented this table, and median survival time, median time to hospital stay is 11, and interquarter range of 7 to 14 days, with the patient without delirium. If the delirium happened, median time would be as long as 21 days. Median time becomes as long as 21 days, and interquarter range being 19 to 25 days. And you may wonder, from your practice, you don't really think people stayed in hospital that long, even though they are sick once mechanically ventilated patient. And what's happening is we obtain this median time based on Kaplan-Meier graph using survival analysis. So median time to hospital discharge is inflated by assuming people who died in hospital still stayed in the hospital and how long they would stay in the hospital. So 11 is really the median time of hospital stay using among patients who are alive and also who are deceased. So for a scientific comparison reason, we like to adjust effective death by truncating length of stay, and this is a correct method. Although when you use this to describe what is happening in hospital, and you may start feeling and something is not really matching with what's happening, and so please be careful.